Good afternoon, everybody. My name is Charlie Nicklin. I'm Chief Executive of IAgrE, and I'd like to thank you all for joining our June presentation. For today's lecture, we hopefully have not one, but three speakers who are very much advanced automotive propulsion experts. We're joined by Steve Whelan, Head of HORIBA's Global Application Centre, based at what was previously MIRA in Nuneaton. We should have Marco Pezzoli, who's the founder and chief operating officer of Soluzioni Ingegneria, if I've pronounced that correctly. And we also have Stephen Child, senior technical sales manager from IPG Automotive. Our speakers today will be talking about vehicle and powertrain development and the use of virtual simulations and digital twins, with, of course, an agricultural bias. As usual with our lectures, everybody will be muted. If you'd like to ask questions, then please pop them in the chat at the bottom of the screen, and then at the end of the presentation, we'll unmute you so you can ask in person. Okay, I'll hand over to our speakers.
Hello and good afternoon, everybody. Thank you very much for giving us the opportunity to present today. I'm going to jump straight in and share my screen. So I've already jumped straight in to share the slide pack that I'm going to present today. So without further ado, I'm just going to press on. So just as the project that we were going to present today was or is a collaboration between three companies, so too is the presentation that we're going to deliver. So as Charlie has introduced myself, my name is Stephen Child. I'm the Senior Technical Sales Manager for IPG Automotive here in the UK. And our co-presenters, hopefully, Marco Pezzoli from Engineering Solutions of Italy and Steve Whelan from HORIBA MIRA. So here is the agenda for the presentation. I'm going to give a brief introduction to IPG, the company that I work for, and then I will set the scene with respect to our presentation, introduce the project that we worked on together last year. And then the majority of the heavy lifting of this presentation will be done by Marco and Steve, who will each present AgriSI and Intelligent Lab respectively. This should take us around 50 minutes thereabouts, and then we'll follow up with a question and answer session at the end. Okay, so IPG Automotive. So we are a simulation provider to the automotive industry. Our customers include many of the largest automotive OEMs and tier one suppliers. So collectively, our software is known as the Carmaker product family. What this software does is it provides the means to integrate prototypes, both virtual and physical, into a virtual test driving environment. So why does an automotive OEM buy our software tools? Because a tool like this saves those organizations money. And it does that by allowing these organizations to left shift their development process. What I mean by that is that these engineers are able to carry out their test work, their development activities, much earlier than would be possible if you had to rely on physically making a prototype and then taking that out to test it. And of course, because we have a virtual environment, there's no limit to the number of virtual prototypes that we can produce, and there's no limit to the number of tests that we can carry out. So this software tool, it's an integration platform. So when the time is right for an organization to start producing physical prototypes, those prototypes can be integrated into this same virtual environment. And what that does is it allows an organization to carry on doing their test activities, because many teams are sort of working slightly independently. The development process may be a little bit different. You will start to produce physical components at different rates. In the past, you may have to wait for different teams to align before you can build a prototype. In this instance, you're able to integrate your physical hardware with the rest of the virtual model and then test it in that virtual environment. So what happens to your virtual vehicle over time? Think of it a little bit like a jigsaw. And as you move through the development process, you're going to start taking out the virtual components and you're going to replace them with their physical counterparts. Over time, what will then happen is that the organization will end up with a full-sized vehicle prototype. But because of the work that's been invested upfront in that development process, the organization can be confident that this prototype is robust and is fit for purpose for the kind of development test that they wish to do in a full-size vehicle in full-size testing. With respect to agricultural applications, our solution is called AgriSI. And hopefully, Marco is going to talk us through how this technology has been adapted to suit the agricultural industry.
Yes, hello everyone, good afternoon.
Hi, Marco. Just
Hi.
a sec, Marco. Hi.
Yes.
All right, one last slide quickly. So the background to the project, so what we wanted to do was to take an existing digital tool chain one that was developed by HORIBA Intelligent. The methodology of this toolchain is to create an empirical digital twin. So what essentially happens is you take an engine in a test bed, you create a digital model, a digital representation of that engine. You then take it into a virtual environment and you test it against representative load cases from that virtual environment. Because this is the case, there's no limit to the number of variables that you can explore. And this means that you can test not just one or two representative load cases, but you can test an enormous number of sample test cases. And the concept is that with this approach, those engineering teams are able to test not just one or two load cases, but they're able to test a very large number, identify those hotspots, those load steps, those test cases in which the engine is going to produce a very high emission state. The concept then is, having identified these hotspots, as we call them, you return to the test bed, you then run the tests in the test bed, confirm that your predictions are correct, and then you move forward and develop your way to a solution. So that's a proven approach with respect to on-highway applications. The objective then for this project was to repeat that exercise, but specifically for non-road mobile machinery, and specifically in the case of this project for agricultural duty cycles. And that then was the motivation for our project. We wanted to offer a solution for OEMs to navigate the challenging stage 5 and the stage 6 of highway emission regulations. So that concludes my bit. And Marco, I know you're there because you've already said hello. So I'll close my screen and let you carry on with AgriSI.
Thank you, Stephen. Thanks. Okay, let me try to share. Yep. Okay, hello everyone. Thanks, Stephen. Sorry for the interruption.
No problem.
Yeah, so my name is Marco. I work in Soluzioni Ingegneria, an Italian company that is partner of IPG Automotive. Today we go directly to the same presentation we did in SIE last year, the prediction of performances and emissions for synthetic machine handling cycle utilizing a powertrain empirical digital twin. So just an introduction, you will have two halves of this presentation. One belongs to AgriSI, our side. It is a software able to simulate vehicle dynamics during off-highway operations. And we will be quite narrow with MIRA, and together to exploit AgriSI to obtain reliable data to feed the HORIBA MIRA powertrain model to evaluate fuel consumptions and emissions. So I will take this first part, so exploiting the simulations in precise agricultural scenarios and providing engine speed and engine torque to MIRA. Agricultural vehicle dynamics and precision farming simulation platforms, co-simulation with IPG, car maker and truck maker. So I will pass in my index through what AgriSI is, some main features of AgriSI, so in a better understanding of the capabilities, data extraction for the digital twin of the engine. So when we work with the tractor and implements, starting from the implements, we, in our software, do model mass inertia, geometry, suspensions, tire over plastic soils, operating limits, movement, kinematics in case the implements make some transformation during operations. So to feed the implement model, we can use a prescription map, that means the target distributions or operations, georeferenced, position, speed, accelerations, movement commands, activation commands, and soil parameters and morphology. The implements model will provide tool soil contact forces, tire soil contact forces, distribution flow rate, PTO torque requirements, demand, hydraulic requirements, reaction forces on tractor interface. So as we reach the tractor, again, we can fully parameterize mass inertia, geometry, suspensions, tire, powertrain. The tractor will handle reaction forces on implement interfaces, PTO demands, hydraulic requirements, driving commands, soil parameters and morphology, and results in contact force beside tires, energy consumption, position, speed, and acceleration. So this flows in an interactive calculation that solves the motion equations of the vehicles and provides data set at each cycle. So let's see in a little bit more in details. So when speaking about tractor, we can build a tractor model starting from experimental or multi-body models if already existing, for example, MSc Adams, through a converter that is quite rapid in developing real-time models. The powertrain can be either ICE or electric and hybrid with dedicated gearbox and drive models. Simulations of dangerous and critical maneuvers, for example, the overturning. I would also say in-field without accounting for seasons. So we have the possibility to simulate every period of the years. Tire model, calibration accounting for plastic soil. And when, as Stephen said before, when we arrive to have some hardware already available, we can jump to hardware in the loop approach. That means having some real components, real ECUs integrated in the loop of simulations. All the architecture is fully parameterizable. You see just an example for on-road scenarios where we see tractor with a trailer in the back where the payload can be changed accordingly. Speaking about tire and plastic soils are quite relevant to the scope, and the tire model have been built starting from experimental data through which we instrumented full tractors with dyno hubs, having slippage, both in longitudinal and lateral, tire slip for tires, yeah, of course, and a force and moment in the wheel hub. Out of the observation of the experimental results, we were able to fit the numerical model in order to respect what the experimental evidence was. This also, of course, considering the formation of tire and soil in slip calculation and rolling resistances for power loss, energy dissipation. The soil parameterization comes through unitary mass, cohesion, properties, and shear resistance. At the end, all this information are used to populate the standard TIR format because we want to guarantee the real-time capability of the software platform. Again, tire can be fully parameterizable accordingly to tire geometry and soil properties. When reaching the implements, we have all the power flow through the power takeoff and resistances force during operations. For example, for the seeding machines, all the resultance reactions under the blades, or thinking about soil tillage, as we will see in a short. The communication protocol between implements and tractor includes most of the standard ISOBUS, CAN bus, or TCP/IP. Control logic of the implements according to precision farming technologies. Again, when the implements is ready, at least with some of the hardware, we can place the full hardware in the loop and try to feed the I/O of the implements through real-time simulations. Before we mentioned soil tillage, so you saw before seeders, sprayer, fertilizer, but we do have also for soil tillage machines. So again, we have the possibility to implement soil parameterization with all the connection to soil, geometry definition, selection of operational depth, calculation of the forces and moments generated during the operation, and all the possibility to run hill. In this video, you see the plow with different depth and generating resistance forces to the tractor. The plow itself can be lifted up, and also all the inertia of the implements is taken into account during simulations, and accordingly to the final position of the implement. So you see the huge inertia, pitch inertia given by the plow. The same can be reconfigured each side, so we can flip the implement side by side and restart the operation so far. There is also soil manipulation, such as the furrow, given by the previous passages. As soon as the blades operates, we will monitor what's going on in terms of where we are, trajectory that we are following, previous furrow, if it is failed, and the new furrow carry. Scenario, we need a georeference scenario. We can import any field in the world, starting from a shape file by the field boundaries, real shape and morphology, possibility to add edge situations such as environment situation or obstacles, vulnerable field presences such as animals or operators, customize and perform beautifications, and try to achieve at the very end stage the digital twin of a farm with buildings, different farms, fields with different soil properties, etc. Control logics, GPS-based, that means georeferenced within the field. This means we needed to perform simulation of georeferentiation of the tractor within the field with latitude and longitudes, prescription maps, importing, and product distribution control. So where the tractor is, it needs to know which is the target flow rate that has to be accomplished in that section. Optimal trajectory importing and generation algorithms, GPS-based longitudinal and lateral control, vehicle control, the CEP for GPS noise injections, and again, as soon as ready, run HIL of any of the components. You see an example of a real field. This is a typical prescription maps giving the kilogram per hectare in the different sections of the field. The tractor is running over a given trajectory. Thanks to GPS, he knows where it is, and we just covered the green zones, and previously it was a yellow one. Again, about control logics, those can be also sensor-based with some sensor fusions, because, for example, we need to have a look of the surroundings occupied by a vulnerable user, or a better understanding of arcs or vineyard plants, whatever. So camera, radar, LiDAR, ultrasonic, definition of position, orientation, field of view, and other related parameters, from ideal outputs to raw signals, target detection algorithms, sensor-based longitudinal and lateral vehicle control for sleep analysis, and again, HIL. So let's see some data extraction that have been done for MIRA. The target was to achieve engine and torque demands, and we ran over different scenarios, for example, fertilizing, comparing soft and compact soil, spraying, flat and hill, plow, effect of depth, seeding with PTO and soil tillage, crop transportation also on public road. I won't go all along the matrices, but just to see a few examples for the fertilizing, understanding the differences between compact and soft soiling. The fertilizing is demanding PTO mostly, so this is the convoy, tractor, and lumped suspended fertilizer with some parameters in the side. And out of a trajectory, we were interested to accomplish a mission of prescriptions. So this is the results of what has been done. And the comparison by means of time histories are vehicle speed that is mostly the same, with the blue compact soil and the red soft soil. The steering angle also is mostly maintained the same, RPM of the engine, that is the target of the controller. But at the very end, you see finally some differences in terms of engine torque demand, Newton per meter, over compact and soft soil. Those will be the inputs to MIRA. So here, briefly, with some good references published on agriculture, you can see what the energy per hectare it was, total energy, and the split between PTO demands or the fertilizing operations and the percentage over the overall energy. So spraying, I would see the second example with flat and hill. The spraying is also making some towing, that means is a semi-trailer in addition to the PTO. This is what we are observing, and the corresponding parameters on the side. Now we are working with constant rate over all the field. And again, we can observe time histories by differences. Again, same speed, same steering angle, same engine speed, but now we have different torque, engine torque, because of the demands we're running uphill or downhill accordingly. You see the elevation in the very bottom. Again, final energy normalized over surface, work surfaces, and the corresponding percentage. We will go through all, and at the very end, we have just a map that is just numbers at the moment, but you can have, I guess, the presentation to better have a look inside in terms of all the operations done, also the plow that is very demanding, and the road expressed in kilowatt hour over kilometer run. So that's all by my side. So I should be on time. I'm available for questions, and I will leave the speech to Phil for the second part. Thank you for your attention.
Thank you. Okay, so yeah, my name's Steve Whelan. I lead a global application center here at HORIBA Myra for HORIBA, our parent company. For those of you who don't know, HORIBA is a multinational Japanese company making measurement instruments, specializing in accurate measurement of all sorts of things. My association with it for most of my career has been measuring vehicle emissions and engine emissions. And at Myra, we've been developing vehicles and powertrain since 1948. So there's quite a lot of expertise here. So without dwelling on the point too much, what we're bringing to the party is our application in powertrain and vehicle development. And what I've been doing with my team for the past 5 to 6 years is developing new applications to streamline the development process. And for that time, we've been working hand in hand with IPG, who've been providing the basis for the vehicle and machine simulation software. We've been developing methodologies like digital twinning of powertrain to enable faster development cycles and get to and powertrain calibration a lot quicker. We originally started this work looking at real driving emissions in the light duty sector, which was a big change for the industry when Euro 6 came along. That's why we started doing this work. And in the past few years, we brought this to bear in the non-road sector because of stage 6 coming in and in-service compliance, which is effectively RDE coming to the off-highway sector. So this is where you don't just develop your emissions for a test cycle. You have to develop your emissions for real-world conditions where the regulatory authorities or anybody, an NGO, can come along and put a mobile emission measurement system on your vehicle or on your machine and test it. And if you don't comply, a whole world of pain will ensue. So we need to be confident that the machine, that the engine produces emissions that are compliant for in-service compliance virtually anywhere in the theatre of operation. So clearly you cannot physically testing everything for that. It will just take too long. If we carry on doing what we've done, it will just take too long and it will be too expensive and it probably won't get done and there'll be a high risk. So our methodologies are here to enable a very thorough analysis to build confidence in the final product without the need for a massive increase in physical testing. So the content of this presentation, one is the introduction. What is a digital twin? In the industry, everybody has got a different view of a digital twin. So I'll tell you ours. We'll show you the digital twin tool set that we developed. Looking at, then we're going to overlap with Marco's presentation, showing you how we built the digital twin and the non-road machine simulations. And then I'll show you some results from combining the digital twin with the tractor model. And then obviously we've got to conclude, because that's what you do at the end of a presentation. So what is a digital twin? So a digital twin is basically a representation of a thing. So it's effectively a digital. Well, I've refrained from using the word model, even though we've got model there on the chart. A model implies a kind of a physics model. this is not a physics model of an engine. So we're not calculating anything. This is an empirical representation. So we run the engine, or in this case, you could do it for any system. You run the system, you change the inputs, you measure the outputs, and then you relate the inputs to the outputs, and that becomes your representation of a system. In our case, we use recurrent neural networks we train the neural network, and the neural network learns. So that's the kind of the sexy bit of AI in there. We train this network, and then we take that and we can use that in other simulations because it runs incredibly fast and it is incredibly accurate within the boundaries of the test. So for some of you who may be involved in simulation, this is not a physics-based model. So we're not calculating the NOx, or we're not calculating the efficiency of the engine. We are literally interpolating a neural network that knows how the system responds if we change the load and the speed of the engine, or the temperature or the altitude. This is what the result is, and you teach the neural network by setting up a structured test, which I'll talk to you about in a minute. So why are we doing it? This is kind of illustrating what I mean, what I said earlier. So graphically, if we say today, stage 5, we have to do a certain amount of physical tests and in-service monitoring. Well, going forward to stage 6, if we rolled our methodologies forward, basically we just have to do maybe twice as many tests or more, and much more in-service monitoring, and to be absolutely confident that the vehicle or the machine, the engine, would remain compliant with in-service testing. So what we're proposing is to use a simulation approach where we can cut down on the amount of testing and overall cut down on the amount of effort. So the bill at the end of it for the bar chart on the right hand side, the bill is a lot lower than the bill for the middle bit, and we get more scenarios. So Stephen mentioned this at the start, because it's in the virtual domain, we can run thousands of scenarios instead of physical tests where we just don't have enough time to run all those tests. So this actually gives you a faster process and lower cost process, because you don't have to pay for physical prototypes or so many physical prototypes, and you don't have to do so many physical tests, but you get significantly more data, so the level of confidence can be higher. But you've obviously got to validate your models. That goes without saying, and we certainly do that. So the digital twin toolset, so as I mentioned, the start of it comes in a test design. So we have to teach the neural network. So we design a transient cycle, and it's got to be transient because we know the state, the NOx emission that will come from an engine. If nothing is steady state these days, a lot of the NOx comes from transients, and a transient going from one condition to another condition. The history is very important, and that dictates the NOx production. So you need to have a transient cycle. So we design a transient test based on how we understand the powertrain will operate in its theatre of application. So that's a crucial part of the process. Then we run the tests. We then take the output of those tests and we put that now into our modeler, which effectively trains a neural network based on all the inputs and all the outputs. And as I said, it is empirical, so it's based on measurement. There are no physics-based predictions in this. Once we've trained the model, we can run the model against measured cycles or virtual cycles, and then we can run those on the engine, and then we can look at predicted versus real emissions, and we can validate we can validate the digital twin. And then as a further step, which is the step we're working on now, which I'm not going to be presenting in this presentation, but we have an auto optimizer that we've been developing with Loughborough University, where this will enable the powertrain calibration to effectively optimize itself, given the constraints. Maybe you want the lowest NOx for best fuel consumption, and this will give you a calibration in hours, not weeks or months. So that's going to be quite revolutionary when we do that. So the way we step through the methodology, so we got the experiment design where we need to understand the application. We develop that cycle, we run that cycle, we produce all the training data, we create the model, we then validate that model, then we move on to combining that with virtual or real scenarios. So as we found with working with many non-road OEMs, these guys have got many real world scenarios recorded already. So in a lot of cases, we can study real world data logs and get predictions from those at different weather conditions, or as we're going to report today, we can generate those scenarios virtually, which obviously gives us the advantage of being able to generate thousands of scenarios, because we can run all this much faster than real time. Then we can predict responses. We can look at those as heat maps. We can look at those as graphs. We can look at those however we like, and we can identify these. In this case, when you're developing a calibration, you can very rapidly look at what we call hotspots, areas of a calibration that exceed the desired level of emissions or fuel consumption, etc. And then we can very rapidly focus in on those areas and eliminate them, and produce a calibration much faster and far more robustly than the traditional approach. So examples of the training cycle. So this is an example. I'll just kick this off. Hopefully you'll be able to see the animation. So basically the chart on the left is a torque curve, and this is the kind of operating envelope of the engine, and you can see the dots going through. So this is the transient training cycle operating, and we run the engine in this way. You can see the transient cycle on the right graph, just going through against time. So we effectively get good coverage of the engine operation. In this case, we've made several digital twins of several non-road engines. And in the case of a non-road engine, it generally gets used everywhere, because it gets used in all manner of different applications. So in this case, we developed a very comprehensive transient learning cycle. So here, this provides all the data that relates all the inputs, predominantly load and speed, but we also stir in things like ambient temperature, and we can also change the ambient pressure on our test facilities here at MIRA using a piece of HORIBA equipment called MEDAS that changes pressure and temperature and humidity, so we can simulate altitude operation and build that into the digital twin as well. So that's the overall approach to generating the data. We then create the model, and then we then take a token sample of data. So we take a cycle. We then run the digital twin across that cycle. We also run that cycle on the test bed, and we produce a result. In this case, we'd look at I think this is, say, yeah, I think this is NOx, but we run the cycles, we get the answers from the test bed, so what the engine produces in reality, and then we also predict it using the digital twin, which is the bottom chart, and then we can compare the two, and in this case, you can see in the black line is measured data The red line is predicted data, and you can probably just about see a little bit of black line peeking through. So basically, in this case, the data overlays. When we look at this on a cumulative chart, you can see this data overlaying. So this is a very rapid validation. Sometimes it doesn't validate, in which case you go back to redesigning the coverage of the training cycle and repeat. The training cycle, as you can see, is in this case is a few hours. So doesn't take very long. So within a day, you can run a test and you can build a model and you can validate it. And then in a few days, you can iterate and get a very, very accurate model. So we can use this to look at any parameters. The next few slides are just showing you some of the data where we've measured it from the test bed and we've used the digital twin to predict. The chart on the left is the non-road transient cycle. So that's a prescribed cycle. The chart on the right is a real-world validation cycle that we developed from real-world conditions. And in this case, we can see fuel flow. So again, very, very accurate prediction of fuel flow. We've then got CO2, which again, that should follow fuel flow, and indeed it does. But again, we're within 1% of predicting CO2 on the non-road cycle and the real-world machine cycle. So again, if you're looking at your carbon emission from your agricultural equipment, this is going to give you very, very accurate predictions. Then we've looked at NOx. NOx is, in the industry, NOx is painfully difficult to predict from any type of simulation. The empirical digital twin gives you a very, very accurate model of NOx within 5%. Sometimes we're even lower. So the real world cycle here is within about 1% from the measured data. So this is extremely good for a NOx model. And then obviously exhaust temperature here, we can predict exhaust temperature. The importance of this, I'm not sure if we show, oh no, that was it, yeah, sorry. Well, also along with this, we can get airflow. So if you've got the gas flow and exhaust temperature, you've got exhaust enthalpy. So if you're developing after treatment systems for your engine, this is exactly the sort of data that you can share with your after treatment system provider and develop the optimum after treatment system to reduce tailpipe emissions. So again, I think I'll be repeating some of the stuff that Marco showed, but so we together we looked at the tractor simulation, which provided engine speed and torque as an input. We combined those with the digital twin, and we produced predicted responses. So these are the five types of simulation, the 5 scenarios we looked at. I won't go over them again. And we effectively produced these. I'll get the little videos running. This just gives you a representation. So, so while the simulation of the tractor is running, you can see. So this is a repeat of what Marco showed you in real time, or in fact faster than real time. We're just slowing it down for you humans out there. We get real fuel consumption, CO2, CO, total hydrocarbons, and NOx predictions from this. So if you want to estimate, what's happening in the real world, if you want to double check, I'll be confident that your powertrain calibration is suitable for a multitude of agricultural operations that could get monitored by the regulators at stage 6. This is the tool that will help you do that without spending months or years in the field with several or a high number of different applications running. So this can all be done, and as Steve mentioned earlier, this can all be done very early in the product development process as well. Once you only need a first prototype powertrain that you can start to get some real data from. Okay, so and looking at that, those are the pretty pictures. This is the hard data behind all those simulations. This is showing the difference between the ploughing depths, and you can see. So I'm not going to go into all this in minute detail, but this gives you objective numbers to use, and you can identify specific operations that may or may not be giving you problems in your calibration. So very quickly you can use this analysis to look at all the different applications that the machine will be running on, and you can spot any particular issues, and you can see directly in the data where your problems are. You can then go back, change the calibration, rerun the digital twin, rerun the simulation, and see if you eliminate the problem. And so once you can measure it, you can fix it. This gives you the ability to do all this very, very quickly at the comfort of your own desk. So the last one here is about the trailer weight. So this is running a road trailer, empty, half full, and full. And obviously, we all know that a full trailer is going to use more fuel and create more NOx, but this gives you the numbers and effectively the quantitative differences between those scenarios. And again, if you look at this data in a different way, so this is using heat maps, and if you're interested in, from a powertrain point of view, where are my problems in my calibration, this shows you the hotspots. So you want to focus your time in improving the calibration in these particular areas for this particular application. It also illustrates, high residence times for a particular scenario as well. So you can, it helps you focus rather than try and solve problems over the entire load and speed range. Also enables you to optimize fuel economy a lot more effectively when you know which areas to focus in on NOx, and you can then optimize fuel economy in other areas. So all in all, when you combine a digital twin, when you have a digital twin, particularly in non-road, where we've just shown the multitude of scenarios of applications on one particular type of non-road mobile machinery, but we know that one engine goes into several, well, maybe hundreds of different non-road machinery examples, and the power of this means you can check or even help you develop like one calibration fits all. At least have that understanding, or if you have to modify a calibration for a particular application and work. If you're an OEM that makes equipment, that helps you interact more, or if you're an OEM that just makes engines and sells them to people that make equipment, you can also double check very quickly that your engine is going to be compliant in the field on a particular machine, because you can work with your customers and they could supply you with models of their machines, and you can use your own digital twin. It having developed this, as I said earlier, having developed this originally for passenger car RDE regulations, we believe this is far more powerful as a methodology in non-road, because the key is you can very rapidly generate a very accurate digital twin of one engine, and that goes in many applications, which is not quite the same for passenger car, where you do have powertrain sharing, but nowhere near the sort of extent you have it in non-road. So overall, we believe this is a very powerful tool, new tool for the armory to help get robust product to market with the lowest possible development cost and the highest possible confidence that it will do what it says it does in the real world and keep keep the regulators at bay. So that's it, really. I won't read through my conclusions. Basically, I've said that all along. I mean, it helps reduce time, reduce cost, and improve confidence. And there's a reference at the bottom of the slide there for the SAE paper. So you can, if you are a member of SAE, you can get onto the website and you can download a copy of the detailed technical paper for a reasonable fee. Okay. Thank you.
Okay, thanks, Steve. What you finished on was the question I was about to type in, actually. And there's a lot of agricultural machinery manufacturers who obviously buy in engines, and the machine manufacturer doesn't have the expertise and so on, so they buy the powertrain in often, you know, a hydrostatic transmission like a sprayer or something like that, where they'll buy an engine in and fit into a hydrostatic transmission. And so is that you can see that being a really useful service for those types of people. You know, because I guess if you're a machinery manufacturer buying the engine, you're very limited to what you can actually do with that engine in terms of its calibration.
Yes. Yeah. Oh, yeah. I'm depending on the size of the customer, I guess. I mean, I'm not involved in the commercial side of non-road, but I mean, ideally, if you're the engine OEM, you really only want to have one calibration. You want to do one development project. This engine meets. So you can, that's what you can do. Up to now, you can say this engine meets stage 5 because you run the non-road transient test, you run the steady state test. If it's going to be a generator, you run the generator cycle test, and they're all reasonably consistent, certainly in the West between the Euro and the US. They are different, but you're not vastly different. So you can certify the engine, tick the box, and that's it. And then it's kind of, you know, there was no in-service compliance. So that's job done. So you buy an engine, whereas now so if you're a machine manufacturer, you'll buy an engine and then it goes out into the field, and at stage 6 it could you know, the regulators, or you know, let's say Greenpeace or whoever, could come along and put PEMs on the digger, on the excavator, or whatever, measure the emissions on a cold morning up a mountain or whatever, you know. There's, you know, roadworks on, you know, Mont Blanc or something, or, you know, they could measure it, or in a hot altitude condition in Spain or somewhere, you know, in some extreme case, which is what's happened. I mean, that's what's driven RDE, is people have been measuring car emissions in various places and saying, hang on a minute, this Euro 5 vehicle is absolutely not meeting the NOx emission it's supposed to, but then it was never designed to. Yeah. So now that's a real world problem when in-service compliance checking comes in, because it's if that engine operates outside its calibration, you know, in an extreme condition in a particular machine, and it doesn't meet the emissions, it still comes back to the engine OEM. So the interaction between the application engineering becomes far more important. And obviously with emission compliance being also in a lot of cases completely dependent upon the operation of the after treatment system, or SCR in particular, then again the application becomes very specific. So that you do need a lot of understanding between what the engine and what the tailpipe is going to do in various ambient conditions under various applications.
I've sort of lost track a bit of where is stage 6 set in place now?
my understanding, and again, don't quote me on it, but and I can check on this, is it's coming in 2032.
Oh wow. Yeah.
So that might seem a long way off, but if you're an OEM, you know, you about now you'd be thinking about starting your development program and looking at your because again, if you go forward with the same stuff, it will just cost more. So you need to start looking at, well, how can we meet stage 6? How can we guarantee it without just doubling the cost of the powertrain?
Yeah, yeah. I guess
So
there'll be
there's a lot of work that goes in behind the scenes.
plenty of machinery manufacturers will have people sitting on committees and things discussing that and having a good idea of what's coming anyway, I guess.
Well, this year I think sees the end of the in-service monitoring. So machine manufacturers have to submit in-service monitoring data. So which is something we've been helping with at HORIBA Myra. We have a PEMS laboratory here. So we do a lot of work on passenger car, obviously for certification, but also heavy duty truck is now Euro 6 now has PEMS, which is portable emission measurement system. So that has to, as part of the Euro 6 approval process, and then obviously even more so at Euro 7. But it's now in stage 5. There's a requirement for in-service monitoring. So it's basically the European Commission mandating data. So manufacturers have to provide independently measured data from their equipment in the field, and then all that data is going to be scrutinized, and then new levels for stage 6 will be agreed, and that's where you get the interaction between the European Commission and the manufacturers' organisations. What is a sensible, achievable limit for for stage 6 and the in-service compliance? So it will then be mandated that you will comply to these numbers, and then like RDE, there could be a threshold of an allowance. In Euro 7, it's about it will be about 1.3 times the NOx of the test is what you must be on the road. So there'll probably be some sort of threshold as a conformity factor for emissions that you need to show that you meet in service.
And if you're somebody like Perkins Engines, who make engines for a whole host of different machinery manufacturers, do they have to provide data for all those different installations?
Well, providing data at the moment, no. It kind of depends. I think it's the machine OEM, the person that's providing the machine, has to provide the data to the EC.
So they'll have to get somebody to come in and measure it for them.
Then, so people like us, there are other companies that do PEMS measurement on cars, trucks, and non-road. But we've been doing a lot of work recently on non-road because of this requirement, which kind of all the data I think has to be in by the end of this year. So there's a lot of manufacturers starting to go, all right, better get on with it. But that's just providing data that will then be put in a big pot to be scrutinised, and then we'll get to some arrangement. And the original stage 6 was a few years ago was tabled for 2028, but I think that the penny dropped a couple of years ago where everyone thought, well, if we don't get all the data doesn't turn up till 2026. There's no way it's going to, 2 years time, it's going to happen. So it got pushed back. Again, that all happens because of lobbying and discussion. At the end of the day, it's got to be realistic. So it's, but at that point, it's the in-service compliance, I believe, will go back to the engine manufacturer, but potentially if the in-service compliance fails, the machine manufacturer could, there's all sorts of penalties that could happen, but you could get a stop production notice. So although it might be the engine, or whatever, but it's not really a finger pointing exercise. Everybody would have to stop. It hurts everybody in the chain. So it's in everybody's best interest to make sure that the machine with the engine complies. But the thing that's, the learning from the light duty side is, to be compliant, you have to take scores of vehicles into different remote parts of Europe and run them round for thousands of miles, because you've got to cover all kinds of driving scenarios, and you do a lot of testing, and it just costs money. You need 50 prototypes, and then you need to take them all around the world. In the case of non-road as well, I mean, they need to work in Europe, but there's also in-service compliance in the US, and it's also going to hit India, for example. We've got a tech center in Pune, and we're already looking at sort of the future of this in non-road in India, because the same thing will hit India in particular. So it's a global thing.
Yeah. Okay. Well, we're just coming up to 2 o'clock. I did actually put one question in. There isn't any questions in the chat anyway, but I just wanted to pick on. Have you been asked to consult on electric powered agricultural machinery at all, where energy conservation is really critical?
Yeah, we'll be doing electrification of the off-road equipment, but again, nothing big. It's kind of smaller stuff, smaller mobility equipment, where it's non-road or military, but nothing big. Again, Ryan Ballard from JCB, as the engineering director, gave a really good presentation at a Future Powertrains conference last year, and you look at the amount of energy you need for big stuff like the big excavators. You can't get enough energy. The battery weighs the same as the excavator. So electrification is good for smaller excavators that may be operating kind of domestically in very sensitive areas, for example, but big equipment takes a lot of energy, and batteries are not very good at storing energy. They're okay for cars, because cars don't actually use a lot of energy. When they're just driving around normally, it's very, very low energy compared to a digger or even a truck. We call them heavy duty for a reason. And they're operating at high load factors, so they use a lot of energy, and it's very difficult to get that energy on board in a battery. So I think you'll see electric mining trucks from companies, and you'll see examples, but in reality, it's kind of questionable, how practical that is, because of the energy consumption.
I was thinking more the sort of the smaller end autonomous electric machines that are starting to appear. There's a lot of things that are sub sort of 1 or 2 ton type machines.
Yeah, well, again, I mean, Ryan Ballard really nailed it, and he said, it's all about energy. It's just all about energy. Don't get yourself wound up with the technology. It's like, well, if you're not using that much energy, batteries are okay. But if you've got an application that uses a lot of energy, and you're faced with putting a 12-ton battery on a 12-ton excavator, then clearly that doesn't work. So it's quite rational. That's why hydrogen, you can store enough hydrogen. It's not wonderful energy storage wise, not compared to diesel, obviously, but you can store enough hydrogen for the larger applications.
Yeah.
So that's where you go with green hydrogen, you get your total, zero emission, zero greenhouse gas solution.
Yeah. Okay. Well, we're just up
That's
to
another subject
an hour now, so I'll draw things to a close. So thank you, gents, for giving us an excellent presentation and taking the time out of your schedules to do so. It is appreciated. I'm sure the video will get watched a number of times on YouTube. So thanks everybody else for joining. Hope you'll join us for our next lecture on the 15th of July, where we'll be joined by Stephanie Berkeley, who is the manager of the Farm Safety Foundation, Yellow Wellies as they're known, and the organizer of the Farm Safety Week, which is running from the 21st to the 25th of July. So all that's left to say is thanks again, and we'll see you next time. Bye-bye.
Right.